Updates to India's motor vehicles rules moved E100 and B100 to the center of the national energy strategy, legally reclassifying them as primary alternative fuels. The shift targets a long-standing economic vulnerability. India's reliance on imported crude oil leaves its market exposed to the price swings of global energy trade. Moving away from those imports has already retained approximately $19.3 billion in foreign exchange. That is capital once destined for foreign suppliers that is now flowing back into the domestic agricultural economy. However, replacing that volume of liquid energy requires a massive expansion in domestic crop output across these primary cultivation zones. This creates a direct conflict between fuel autonomy and resource preservation. The overlap here shows where mass cultivation for ethanol places the most strain on India's critical groundwater aquifer levels. Solving this complex challenge requires striking a delicate balance between rigid mechanical engineering and the absolute physical limits of agronomy. The transition to E100 is a precarious balance sheet problem, demanding equilibrium between macroeconomics, engine design, and water management. E100 is rarely pure ethanol. It is composed of 93 to 95% anhydrous, or water-free ethanol, with the remaining volume consisting of petrol and solvents. That small petrol fraction is an engineering necessity. Pure ethanol has a higher ignition threshold and burns with an almost invisible flame. The petrol ensures a reliable start in cold weather and makes the flame visible in an emergency. The physics of this chemistry presents a challenge. Pure ethanol contains roughly 33% less energy per liter than standard petrol. For the driver, that lower energy density results in a 27 to 30% drop in total mileage. Standard internal combustion engines cannot run on this mixture. Anhydrous ethanol is highly corrosive. It rapidly swells and cracks the nitrile rubber seals and hoses used in conventional fuel systems. Survival requires a dedicated flex fuel platform. These vehicles use stainless steel fuel tanks and corrosion-resistant FKM or EPDM rubber seals to protect the engine's integrity. Because the fuel holds less energy, the injectors must be larger and stay open longer to deliver the volume of fuel required to match the engine's power needs. The engine control unit also requires specialized recalibration to manage ethanol's high octane rating, which typically ranges between 100 and 110 RON. An E100 vehicle is a distinct mechanical system built to withstand a low-density, chemically reactive environment. Adoption depends on the math at the pump. Drivers won't accept a 30% drop in kilometers per liter unless the price of the fuel compensates for the loss. To reach cost per kilometer parity with petrol, E100 needs to be priced at or below 70 rupees per liter. Despite the policy push, domestic ethanol plants are currently operating at only 35 to 40% capacity. This underutilization isn't due to a lack of domestic manufacturing capability. The friction is in the distribution. Anhydrous ethanol is moisture sensitive. It requires a specialized moisture-sealed infrastructure to prevent fuel degradation, a network India is still building. The government's rollout plan begins with 150 pilot stations in major metros like Delhi and Nagpur, with a goal to expand to a 5,000-node network within 24 months. Without a moisture-sealed distribution grid and strict adherence to the 70 rupee price ceiling, the engineering behind flex-fuel vehicles remains economically out of reach for most consumers. To understand the ceiling on this program, we have to look past the refineries and down to the agricultural source. Currently, sugarcane juice-based ethanol has a production cost of about 65 rupees per liter, which fits within the consumer pricing threshold. But sugarcane is one of the most water-heavy crops in cultivation. Relying solely on sugar to scale E100 places an immense ecological burden on India's already depleted groundwater aquifers. Maize is the primary alternative intended to lower that water footprint. While sugar requires a high volume of water for every liter of ethanol produced, the water footprint for maize is significantly lower. However, maize is more expensive to process, with production costs currently hovering around 72 rupees per liter. This crosses the 70 rupee threshold required for consumer parity. For producers like Sri Renuka Sugars, this creates a margin squeeze that makes maize-based ethanol difficult to scale. Mills are forced to choose between producing fuel at narrow margins or selling sugar for food, where profits are more secure. This reliance on food crops creates a systemic trap. Sugar drains the water supply, while maize makes the fuel too expensive for the consumer. Breaking this cycle requires moving beyond food crops before the E100 program reaches its ecological limit. Advanced second-generation or 2G feedstocks, like Napier grass, provide a high-yield fuel source with a minimal water footprint. Agricultural waste, such as rice straw, also offers a massive resource, turning existing farm residue into high-grade fuel. The process is technologically complex. Instead of fermenting simple sugars, refineries must chemically break down tough cellulosic walls to reach the fermentable material. Specialized engineering firms are now working to scale these 2G technologies to commercial levels. Compressed biogas, generated from organic waste and pressed mud, provides a parallel solution to broaden the alternative fuel supply. These methods achieve a critical goal. They decouple India's fuel production from its water-intensive food crops. 2G biomass is the only pathway that can satisfy transportation energy needs without compromising the nation's water or food security. E100 offers a genuine route to energy security and domestic autonomy. This transition depends on balancing macroeconomics, engineering, and agronomics. Automakers must scale flex fuel production for corrosive anhydrous ethanol. Retailers must deploy moisture-sealed infrastructure to maintain the 70 rupee parity mark. Finally, agriculture must shift toward 2G biomass to protect the national water table. If any of these pillars fail to materialize, the entire ecosystem collapses into either an economic or ecological deficit. India has the capacity to replace imported oil with domestic agriculture without triggering a water crisis. But success relies on policy. The strategy must move past first-generation crops and pivot fully toward non-crop biomass technologies.